Hello to my new video in Grasshopper. This time I'm using only Karamba and making a simulation of a unreinforced concrete wall. First, let's mention the border conditions. We have an interior wall which is supported both sides, top and bottom, and gets dead and live load from the floor slab. In order to design a wall as unreinforced with Eurocode 2, we have to limit the slenderness ratio to 86. And here are the formulas which are used to reach that. Okay, welcome back. Now I'm in Grasshopper and I'm starting to build this wall using only Karamba tools. I need the Higgs Z plane. And let's say the wall will be width 1 meter and height 2 meter 80. For the mesh density, let's get 20. Now this was the parametric from Grasshopper. Let's go straight to Karamba. I'm going to need create surface element in Karamba. This is the mesh and cross section. Let me turn on the components and just the cross section component. I need a shell constant cross section with the material concrete. Let's say it will be C2530. This goes to material, this goes to cross section. And the height of the plate of the wall thickness will be 20 centimeter. I will prepare first my components for Karamba. I will have a load component. Load component will be point load distributed of the top on the top of the wall where the slab meets the wall. And I'm going to have two support components for the lower and for the upper supports. Then we're going to analyze and first assemble the model. Let's get started. First, I want to extract the points from this mesh and with some conditions to separate which are the bottom, which are the top supports. First, I'm going to remove duplicate points in case there are any, and want to get these points. The easiest way, I think, is to deconstruct the point. Get the Z value and compare it to 0 for the bottom, and ask if this is smaller than 0, and if it is, we call these points. Okay, now I see the points that I want and input them here. For the upper points, let's write here for the upper supports. I also want to deconstruct the points. And here let's try other approach, sort list. starting from the bigger value for 2.8 meters. And compare again this value with all of the z values, and again curl pattern. This gives me the other top points. Let's take a look to the load. Okay, I want the load to be distributed in each of the nodes on the top of the wall. So let's first define the direction. This will be negative z. As that load, I will use 350. Sorry, as this is from the slab. The coming load from the slab is the dead load plus the live load as design loads, and I'm going to add the self weight of the wall, which I decided to make with formula. Getting the thickness of the wall, which is going to be T, and the height of the wall. I'm just adding the both values. And connecting to my unit Z. And because this wall is too big and it will be distributed between all of the points, I want the least length of my top points. And dividing the load by the count. So I have in minus z minus 17 as force kilonewton. The next thing I'm going to do, I want to calculate this moment, because there is right now no opportunity to give automatically this eccentricity from Caramba. There is also only beam eccentricity. So I will try to do that by calculating the moment beforehand. And as I said, the wall is getting the slab load with eccentricity. And caramba, there is no possibility right now to give shell cross section with eccentricity, so I will write manually the formulas to find out the moment on the top of the wall, and then the eccentricity as consequence. And here I've written already the formula. This will be the load, the line load, times the thickness of the wall in meters, divided by 6. So I'm getting this moment in kilonewton meter per meter length. And then if I divide the both moments and divided with distributed load, I'm getting the eccentricity in meters. But I need this moment to give caramba, to let caramba know that we have also not only compressed wall but also bending moment. So I also divide this moment by the number of nodes. I'm getting something like this per point per node, and I'm going to put this here. Okay, it wants to be vector, so what is the direction? So along the wall I have x axis, so I have to put this here, and the other one are zeros. Okay, now I need the positions ID for this wall. These are the upper points here. Okay, now I can try to assemble my model. The both groups of supports are getting here. This is my element, and this is the load. Let's just flatten this. Go to analyze model. Let me just check something. Buckling modes. Okay, no, it's I didn't give the support conditions, of course. So let's see. The bottom, I want to fix all the translations and also one rotation, because the wall will be rigid and can flip otherwise. And on the top I will fix only for the slab, the direction perpendicular to the wall. And now if I check this buckling, okay, it's bigger, so this is the buckling factor, which if I multiply it with the normal force, then it's there is stability problem. Okay, so now I want to visualize some results, what I've done. This is the view, just switching these names. And for the mesh, then I need to see the shell view. Here are my support conditions. I also see the deformation. Okay, I see the deformation and slightly bending. I can see the moment vectors in each point and the vertical load in each node, and also that I've taken these points from the element component, and these same points are extracted to apply the supports and the load. So this is very important that the points are part of the mesh. This is my side fixing of the wall. Let's get further. I will be interested in stress strength ratio. I can see that the wall is 36% utilized. What else can we show? We can show the normal force. For this I will need shell section. in y direction I want to see the results. So here I can visualize the normal force, let's say, minus 300. These are the different heights of the location of these results. They are changing slightly. I changed the scale, and these are the results. This was all for this simulation. I hope you enjoyed it, and I'll see you in the next video. Bye.